Thank you for coming down. But my neighbour, you know, is a car enthusiast. During the week he drives around in a very modest hatchback, but for weekends he's got not one but two red sports cars, one for himself and one for his wife. And he spends an inordinate amount of time, and for all I know money, working on these cars. I think that's great. I think a man should have a hobby. I don't need sports cars at my time of life. This is my hobby. And I decided that I would put together a bit of a requirement specification for a tool for my workshop. So I decided I wanted a mill. I mean, NC turning is terrific. It's great fun. It can be quite scary sometimes. Mills are more flexible. You can make more stuff on the milling machines. And I wanted a quotes, proper mill, not a woodworking router. Now don't get me wrong, people do really good stuff on woodworking routers, but I wanted to do metal work. I decided we would have 3 axes, although I would really have rather liked 5 axes. Life's a bit short. And it had to be well affordable, yes, and it had to be something that I was going to get done. I didn't want a project that was so advanced I never finished it. Had to understand how it worked, and because who else is going to maintain it but plugins here. And it's got to go in my garage that I dignify with the term description workshop. So, are we going to make this thing or are we going to buy it? Well, I did a little bit of research quite early on, and several of my customers, when I was alive, had milling machines made by a company called Haas. You might have come across them. They run a Formula 1 team, but their background is in milling machines, CNC machines, simple, robust, and I was told relatively low-cost milling machines. And they make a small one, which they call their tool room machine. It's got a small footprint, but otherwise it's similar to the industrial ones. So that's the machine in question, and those of you sitting near the front can probably see why I didn't actually go for one of those. My buddy who runs this IBI company, the Belgian company, his CNC machine cost him $3,500 on eBay. It's far too big for my workshop if it was for sale. And it's very, very tired, as you see. I mean, I was telling you in the first half that he does all these spindles, these shafts for the rollers, works a treat for that. The machine, when it's a bit like Inspector Morse's Jaguar. When it was new, it was best in the business. These days, it's a bit tired. So that was about $3,500. That's another customer machine. It's a Bridgeport-sized knee mill. He paid a lot more than 1,800 quid for his, but you do see them change hands for that sort of money on eBay. Who knows what sort of condition they're in. And it's still a little bit on the big side. So I thought, well, okay, can you get a smaller one? Perhaps you buy a small machine that's CNC to start with. Well, I'm not paying that, because if you look inside that enclosure, it's just got a quite ordinary Far Eastern made 3-axis milling machine that they've converted to CNC for training. So, as I say, it didn't take me very long to decide, I'm going to do this, I've got to make it. Well, I didn't fancy buckling down and fabricating the frame and all that stuff, so the sensible thing I thought was to start with a manual machine and to convert that. And this is the type of manual machine that I've ended up with. These round column mills are made in the Far East. They're imported by, as you see, Warco, but also by Axminster and Chester Machines. And they badly given their own names, but they're all made by this company called Rongfu, formerly of Taiwan, and these days I think mainland China. And they're not actually desperately cheap if you look at the top of the screen, but that was the sort of machine I thought, well, yeah, perhaps something like that would do. But I'm not paying 1,300 quid. This sounds a bit cheapskate, but in the end, I bought this on eBay. Those of you who are eBay users, you'll know that you can buy stuff new, you can buy stuff used, you can buy stuff spares and repair. Well, that's what this was, 510 quid, but it's a metric machine because they come in either metric or imperial. I preferred the idea of metric. And the spindle taper is an R8 taper, so it's the same as a Bridgeport. So I could use the same tools as I use on the Bridgeport at the Bedford Club. So yeah, bought that, and I knew when I bought it, it was advertised as bits missing. There was no motor, so I had to get a motor organised. I had to fabricate a motor mount, buy all the belts and stuff to transmit the drive to the spindle, replace the spindle bearings because they'd gone beyond it. So all straightforward stuff there. Then there was the rack component. I don't know, has anybody here got one of these round column mills? I don't know if you've come across them. I suppose it's quite a clever design feature in a way. It goes like this. Look, if I'm using the Bridgeport at the Bedford Club, and I've just used a short cutting tool, and now I want to use a long one, I've drilled a hole, and now I've got a tap and a tap follower and that. Then I can lower the knee and take the table down so I get some more daylight under the spindle. Well, I can't do that on my machine. This isn't my machine, but it's the same type of machine. You can't do that because the table's fixed. What you actually do is you lift the head up or down on this round column, and there's a rack and a pin that you can just about see the handle there. You slacken off some logs on the other side, wind that handle, and the thing goes up and down. And that rack is not fixed to the round column. It sits in a groove like a gutter at the bottom on this circular component. And in a way that's quite clever because like on a pedestal drill you can slacken everything off and tip the head round and drill here down beside the table, there beside the table, which is fine if you want to do. I don't want to do that. In fact, if you don't mind, I'd like you to stay put. But anyway, none of that was an issue at first because I didn't have the rack at all. It was absent when I bought it. And of course I didn't know exactly what size I wanted. And I messed about and did some quite primitive measuring and decided that I probably wanted it that long and that wide and that pitch. And how am I going to make one of those? Do I know anybody with a horizontal spindle milling machine? No, actually I don't. In the end, I phoned up Warco's spares department, and they were a bit sniffy, and they said, we only sell spares for Warco's, and yours isn't a Warco. I said, no, listen, chaps. And after a bit of toing and froing, they said, well, I'll tell you what, on the shelf here, we've got a rack, we don't know what it's of, and it's all a bit rusty, and you can have that for 20 quid. So I bought that and it fitted. So that got me out of the garbage. But then there's this business of the head flapping around when you release it, and that's what I wanted to do was grossly unsatisfactory. So up at the so the first thing I did was I drilled and tapped some holes in this and screwed the rack onto the column in a fixed location. Which then meant that instead of being able to swing this thing through 360 degrees, it only went a couple of degrees. And then I invented this really crude gib thing to sort of lean against the side of the rack, and it's not very good, and it's not up to the standard of the rest of the machine, and I still have to re-indicate it when I lift the head up and down, but at least it stops it flapping around in the breeze. Now, if you have problems of your own, I've got a round column mill. If I was doing this again, or if you ever want to make a CNC machine out of a manual one, chaps, don't start with a round column mill, get one with proper sides up and down. Learn from experience. What else? Oh yeah, the column, the round column that I've just been grumbling about wasn't perfectly perpendicular to the base of the machine. I'm not making this up, you know. So I took the base into the Bedford Club and milled the feet and then milled the top flat, and I took the column into IBI and scrounged the use of their very big lathe and got the column in there and faced the end of the bottom of the column, so it is now perpendicular. Thank you very much. And then I was just going to put it all back together, and the V-belt pulleys, of course, have got a different hole size to the electric motor that I bought. Well, easy enough to make a new diameter in there, but I also had to invent this ugly homemade tool here to sort of slot a new keyway in there. We do have fun, don't we? So, at this stage in the proceedings, I'd reached a milestone. I'd got the milling machine back together. That's not my milling machine either, that's a stock photograph. 8 months into the project, and the mill's working from the handles. Nowhere near CNC, just working from the handles. Well, anyway, I was pleased with that. And I'm a bit OCD about these things, and by this stage I'd spent 770 quid, including the 50 quid that I paid Pallet Line to bring the thing back from Hampshire to Letchworth for me. So, yeah, doing all right. And at this stage, then, start to think about what are we going to do about CNCing this. Well, I decided that I was going to use stepper motors rather than servos. Looking at what hobby-type people do on YouTube, they by and large use stepper motors. If you've not come across stepper motors, then I'll pass this one round. This is smaller than the ones on my machine. They come with certain frame sizes and NEMA numbers. I think it's a NEMA 27, is it? I don't know. But interestingly enough, it's defined by this flange on the front. And if you want one that's more powerful, then the flange is the same, but they make them longer. So they're more powerful and generate more torque. And if you've not come across this, I'll pass that round, and if you give it a twiddle, you'll feel that there's you'll feel inside the rotor is rotating near a set of magnets. Yeah, so that was one I bought for a bit of prototyping to make sure that I was happy that I was going to be able to drive proper ones. I bought the proper ones from this company called CNC4U, who are based in Milton Keynes. I don't know much about them, but they seem pretty helpful on the phone, and I had a couple of conversations with one of the guys there, and they'll sell you all the bits and pieces separately, or they'll sell you a kit. This is the kit for medium-sized hobby messing about milling machines. And as you see, there's 3 biggish stepper motors. These black things beside the stepper motors are the stepper motor drivers, and more about those in a minute. And then this circuit board at the back, didn't actually use, don't need that, and underneath there's a silver box as a power supply, and you can buy the whole thing from from a supplier like them, and you know that they're all going to work with one with another. So I had to invent some way of mounting the stepper motor onto my lead screws on the machine. Now this picture shows the inside of the handles on the machines that control the axes. And you see there's this sort of dog clutch arrangement there, and that goes straight onto the end of the lead screw as manufactured. And what I did, and I would love you to think that it was my idea, but it's not, it's reverse engineered from, that's a posh word for copied, from a commercial product that I stumbled across, and made these bits, specifically the bit on the right hand side is an extender, and you can see it's got the dog clutch teeth on it, and it fits in there. I don't know if you can see what's going on there, but that's the cylindrical bit. There's the dog clutch going onto the original lead screw part of the machine, and then out at this end there's some other gubbins, including the gear wheels, more on those in a minute, and then there's the original handle on the end, because I made I made these little things to go right on the end so that the original handles could fit on. Something that I failed to do when I made my requirement specification, but again, a bit of gratuitous advice. If you want to do this, try and make arrangements that you can keep the original handles on your machine, because then you can use it as a manual machine, or you can use it as a CNC machine. So what then happens is there's all this scaffolding holds the stepper motor in place, and a couple of there's the thing I copied, picture of the thing that I copied, available for sale in America, that's me making the, well, it isn't me, but I'm making the plates that hold the stepper motor a certain distance from the extended lead screw. Obviously the centre hole distance is vital that you get it right there. So,
can you disengage the stepper motor?
No, it's permanently engaged, but when it's powered down, then when I move it, you can feel it actually cogging over very slightly, and that's actually an advantage. It sounds like a disadvantage, but in a minute you'll see why it's an advantage. It's permanently engaged. When you turn the drivers on, there's a bit of a clunk and nothing moves. It's absolutely rigid. They're holding the thing still. Yeah, so it's those plates there control the centre distance between the two shafts. And on the far picture there, you can see I've got not one, not two, but three dial indicators set up to sort out the centre distance. And we're never short of encouragement and comment at the Bedford Club, and you see there's not one, not two, but three club members saying, "Not sure I'd do it that way, John." Supervisors. So,
what did you do to eliminate backlash in the gears?
There's precious little backlash in the gears.
Yeah.
Of course there's some, because there always is in a gear drive. And other people have used toothed belts, which apparently have no backlash. I suspect they probably have a bit of stretch, don't know. But the backlash in the gears has not been an issue, but I will be talking some more about backlash in just a minute, if you bear with me.
Yeah.
So this is three of the chaps actually at Bedford who are encouraging me now in. There's me plates made in the far picture, and here I am on the rotary table cutting the dog tooth arrangement on my extension pieces. And these are the gears. I bought them. I bought them from a company called R.A. Rodriguez. With a name like that, you'll be surprised to learn they're actually a German company. And their sales outlet is round the back of Sainsbury's in Letchworth, so I was able to actually go around and see them and get the things. And they weren't low cost, but they've been good. You know, they seem to be accurate, they've worked first time. I bored out the centre of one, maybe both of the gears, and they've worked a treat. And there's my arrangement, and I can still use the hand wheels, which is good stuff. All right, so that was that. So that was the mechanical bit. Now what about this controller business? We've got the steppers, we've got those big drivers that we saw in the earlier photograph, and there they are. Now, we need somehow to get our NC program down to the stepper motor drivers here. They are just like big amplifiers. Talk a little bit more about them in a minute, but we need to get step and direction instructions to those. And reading up on hobby-sized milling machines, then most people who've done this use a proprietary program called Mach 3. There's one actually called Mach 4 now, but same stuff. And it runs on any old PC hardware. The computer blokes amongst you, it actually runs under DOS and not Windows because it's got to be real time. And if you're not a computer bloke, that means you can use any cheap old PC you choose. And you've got to pay for Mach 3, and it's not that I'd be penny pinching about this, but I thought, well, okay. Yeah. That was the fallback situation. If what I did had not worked, I would have bought a license of that to get myself out of the garbage. But I'm well and truly out of my comfort zone here. I was talking to one of your number at the interval, and I must emphasise that I knew nearly none of this before I got involved in this project. I am no sort of expert. I just know enough to make this work. So these drivers, what goes on there is we give it step and direction instructions on one side, and those are at low voltage and probably no current, next to no current, and the steps say move a certain distance, and the directions say no, go the other way. And they're tiny, tiny little instructions at the type of voltage that you get out of a computer. I said there'd be computers in the distance, didn't I? But they're well under control. And this thing amplifies it, and out of the other side of the drivers is a stonking great pulse to drive the stepper motors, 30 to 40 volts or something, and I don't know how many amps. I mean, I did know at the time, but I've been to bed since then. So we need something to provide these step and direction pulses based on the NC program. And what I chose to do was to use a program called Garble. I'm not making this up. The program is called Garble, and it runs on a computer called an Arduino. Now, before I started, I had no idea. I'd never heard of Arduinos. It's a computer. It looks like that. Here's one. I'll pass it round. It's a computer on a circuit board that is a little bit bigger than your credit card. These things are cheap as chips. Less than 10 quid. But what do you mean it's a computer? It hasn't got a keyboard, it hasn't got a screen, it doesn't appear to have any sort of data storage. What do you mean it's a computer? But it is, and and you can program, well, you can program it, I can't. The people who wrote this garble program have written the program. It runs on this tiny computer. You dribble your program in on a USB port, like the one that my mouse is attached to. You send the program down that, and it sends out step and direction pulses out of dedicated pins at the back. All those multicoloured wires go into my drivers, into those black boxes at very low voltages, 5 volts and 12 volts, whatever it is, and the drivers pulse out the stonking great pulses that are needed to drive the electric motor. Now I've told you that, you know as much about it as I do. Well, we'll give it a go. So I got hold of an Arduino and I did some tests with it, and I connected it all up to my drivers. And this slightly messy diagram, I've tidied it up since, but this slightly messy picture here, you can see the Arduino down at the front. You can see the 3 big driver boxes there. You can't see the power supply because it's out of shot at the end. There's a couple of fans here that used to belong to an old computer to blow air across it. And this board here generates 12 volts or whatever we need to drive the fans. That was the most advanced bit of this. The rest of it, I just plugged it in. And remember that picture because we'll return to it later. So we were nearly ready to test this. Nearly ready to test it, except on that sketch earlier on where it was saying this pin does step and this pin does direction and yada yada. There's also a couple of pins that say, do you know what, it'd be handy if we had limit switches at the end so that when I turn this thing on, it can go along and find out where it is, or if I make a mistake, because we make mistakes, if it bumps into a limit switch, it just stops. And again, forgive me if you know all this, but there's a tiny limit switch, and there's a rather better one, an industrial sort of quality limit switch. So I had to get those organised and put them on, and you can see some rather crude Meccano engineering going on here on my Z-axis. When the quill comes up, then that rod goes up, complete with the adjusting nut on the top, and it hits the arm and it pops the limit switch, and then the garble program knows where end of broadcasting is upwards. So it knows not to go beyond that, and if I try and program it to go beyond that, it'll just throw an error rather than clunk into something and do some damage. So there was a certain amount of messing about to get that done. What else did I have to mess about with? Oh yeah, I said these Arduino things, they are computers, but they've got no screen or no memory or anything. And you want to send down your NC program saying go here, go there, stop, turn the spindle on, turn the spindle off, all that. So you need to get some cheap and cheery computer to do that sending. This laptop literally came out of a recycling bin. And on it there's a program which rejoices in the name of Universal G-Code Sender. Forgive me, I should have told you this earlier on. G-Code is another name for the NC program. Just a name. Universal Program Sender, if you like. And that thing sends the instructions down to the Arduino on demand. And the Arduino will be there saying, hang on a minute, I'm just doing that. Now send me another instruction, I'll do that one now. And so I had to get this thing lashed up, and you see I've got these brightly coloured bottoms on the front there. Green for go, amber for hang on a minute, and red for no, don't do that. And as well, on the machine itself, I've got a black and grey e-stop that kills power to everything, just in case. Right, so I'd done all this stuff, and I was feeling pretty chuffed with myself. Got all that going, John. Ready for the great switch on. Do you think it worked first time?
No.
It worked second time. And if I hadn't been in a rush and wired the step and direction across, it would have worked first time. Now that's not a reflection on me, it's a reflection on how straightforward this is if you can be bothered to read and stay awake. So at this stage, it was working, it was cutting things. I was making, look, I'll pass that round. I was going and getting people and saying, come and look at this, I told everybody who'd listened to me how clever this machine was. Really, really pumped. So, how do you reckon it's going? Well, this is where we got to the challenge stage. Yeah, this is where we got to the problem solving. Quite early on in the history of the machine, I had occasion to make this thing, or a couple of these, for a buddy of mine, an ex-colleague, who is a beekeeper. And this is out of a centrifuge. I don't know anything about beekeeping, but I understand he goes into the middle of the field, empties honey out of the insides of the beehive into a thing and then spins it up to centrifuge it out. And he said, oh, you've got your little machine going, can you make me one of those? So, yeah, sure, I can make you one of those, that'll be fine. It didn't work out terribly well. And the reason it didn't work out terribly well is that there was about 20 thou, half a millimetre of backlash on the lead screws that came with the machine. Now, if you're driving the machine by hand, you can cope with 20 thou of backlash. But if you're driving it by CNC, then if you're trying to make something precise, it really doesn't smoke it. And subsequently, I haven't got a picture of the part that I made with all the snaggled teeth. It was just embarrassingly bad. But subsequently, I faked up these pictures to show you on the far side, on the left-hand side, what it looked like as programmed, and on the near side, on the right-hand side, the sort of tool path that the machine followed, because every time it changed X or Y direction, there was this lost motion. So, oh dear, I'm not very pleased with that. What do we do? Well, what we did, the reason, I'm sure you probably know about this, the reason there's the backlash is because in order to make this work at all, you have to leave a space between your lead screw and your lead screw nut. And you try and keep it small, but there's going to be a space, and that's going to manifest itself as backlash. And what you really want, and what industrial machines have, are, instead of lead screws, they have ball screws. Now, if you've come across these before, then forgive me, and if you haven't, then it's a bit like a ball bearing that's had a fight with a spin dryer. The screw itself, the screw component itself, is quite coarse, and on an industrial machine that would probably be ground. And the ball nut is longer, and inside the ball nut there are a load of balls, like in a ball bearing, and as that rotates, as they rotate one relative to another, then the balls end up at one end, and then inside the ball nut there's a sort of escape route that the balls follow, go to the other end and start again. It's slightly black magic. If you're familiar with these things, you know all about it. If not, then have a look at this, try it for backlash. Please don't screw it off the end because all the balls will fall off on the floor. And that one going round, although it's a bit rusty and tatty, is a high quality one. And they always used to be ruinously expensive. However, these days, everybody and his dog makes 3D printers. And so small-ish ball screws are actually relatively low cost and very, very available, and made in the Far East. And these will have rolled rather than ground screws, so they're not going to be as precise as an industrial one, but they're still pretty good. And what I did was I treated myself to a couple of ball screws, complete with ball nuts and all that good stuff, and I made up an adapter. And again, this is something that I would love you to think that I designed or invented this design myself, but again, it's something I've copied from a commercial arrangement where somebody sells something rather like this for putting ball screws on your Bridgeport manual machine, a big machine. And so I made these adapters, and the ball nut goes into this cylindrical hole here. The ball screw is 16 diameter, and that's 17, so that goes through there nicely. The ball nut screws onto this flange, and on the outside here I put a screw thread that I could screw into the pre-existing nut that was part of the lead screw arrangement. The original lead screw was 23 and a bit diameter, so the ball screw is smaller in diameter, but this thing mimics the original lead screw. I then screw it into the nut, and yeah, there's a 3D rendering of what I made. So my bit is the green bit, the yellow bit there is the ball nut, the purple bit is the ball screw, and the rest of the stuff here is the table and what have you. And here's the bit in the flesh, the bits in the flesh. Yeah, so I think you can probably see that that ball nut there will fit into that recess there, and some screws through there will go into those holes there. And this bronze jobby is part of the original machine. It's the thing that rode on the old lead screw. And what this design allows you to do is you screw my homemade adapter into there. There's this crude thing that was designed originally to reduce the amount of backlash by sort of compressing the screw thread rather horribly. If you want, you can just do that up tight, or you can put high strength Loctite on there, or you can do what I did and do both. There was a certain amount of messing about. Here it is being assembled. I'm using the table of the Bridgeport at the club as my assembly table there, and there's some of the bits and pieces. Oh, at the end here, yeah, the end of the shaft that all my handles and stepper motors and stuff fit on is actually bigger in diameter than the ball screw. So even if the ball screw wasn't hard and very difficult to machine, I wouldn't be able to machine it down to that size because it's already bigger. So I made this extension piece like this and fitted it onto the end of the ball screw with that. Anybody recognise what that is? It's a 15mm plumbing fitting, yeah, done up really tight with an olive in there and another handful of high-strength Loctite. Needs must. Right, so did all that, and mirabile dictu, we ended up with about 3 thou of backlash instead of about 20 thou of backlash, and I suspect, but I'm not sure, that actually that's probably not backlash in the ball screws, it's probably backlash in the bearing, the thrust bearing that constrains the ball screw at the end of its travel. And here's the replacement, or here's an example of the replacement gear wheel that I made to unembarrass myself. So there we are, that was good, and I felt better about that when it was done. Alright, so that was the first problem that I thought might amuse you. Now this will get you going. The Universal Program Sender program that dribbles the instructions down to the Arduino, to the Garble program, should just go, here's an instruction, and it then waits for an acknowledgement, and it sends another instruction, and it waits for an acknowledgement, waits for an acknowledgement again. However, I noticed that from time to time, it would throw an error. And it would do that when I switched on an electric motor on the other side of the workshop. I'd be running a long program, letting it go, and thought, well, that's good, that'll be all right. Go over there, switch the linear on, and the thing would fault. So I thought, well, that's not very good. So what did I do? I went down to town with a screw fix and bought one of these extension lead things, a bit like this, but with a filter in it. Not going to do any harm, is it? I went round and made sure everything was carefully earthed. The limit switches, I replaced the cables on those, and I used the type of cable that they use on satellites instead of the type of cable that they use on front doorbells. And I got a job lot of these ferrite core things and wrapped the cables through those. And I thought, well, we'll see if that makes any difference. And it didn't. It didn't help at all. So at that stage, I went to the pub. I actually went to the pub with a school friend of mine, who's a very clever man, and runs this engineering consultancy in Cambridge, and does a lot of electronics and difficult physics, and explained the sort of problem to him, and very, very kindly, he came over to Letchworth on what must have been the coldest day of the year, and brought his oscilloscope and plugged it into the back of the works and said, right, well, go over there and throw the switch. He said, you're working with a 5-volt signal, aren't you? I said, yeah, it's supposed to be 5 volts. Yeah, when you do that, I get an 11-volt spike on the line here. All right, what do we do about that? Well, in the pub, he'd already drawn these on the back of a beer mat and said, what I think you're going to need is that. Now, I'm out of my depth with this gentleman. I'm not an electrical bloke at all. But he said you're going to need a load of capacitors, you're going to need some inductors, you're going to need ferrite cores. I said, I've already got ferrite cores. And he issued. I'm sorry?
You've got a Zenodiode there.
Yeah, it looks as though I have. Can't remember, it's Bedson's thing. But anyway, bless his heart, he issued me with all of these bits and pieces. I mean, I said, no, I'll buy them. Ah, let me daft, I've got them. Well, I'll buy them from you. No, I get them both. So you probably remember that my Arduino looked a bit like that before, with the cables plugged into it. And I got hold of one of these circuit boards. It's the same footprint as the Arduino, but it's just strips of connecting connectors on the circuit board so that it's easy to solder things up and right out of my comfort zone. Yeah, here are the, I think the big components are inductors, are they? I don't know. And you see that circuit board is designed with pins on the bottom, so you can pin it in the top of your Arduino and add extra electronics to it. And I made all this, and I double checked it, and then I triple checked it, and then I plugged it in, and it looked like that. But do you remember I said, please remember this photograph earlier on? Well, that's what it looked like when I finished. Components everywhere, wires everywhere. I have tidied it up since then. And we got the oscilloscope on it again, and he said, you've still got a pretty hefty spike on that, you know. But it's better than it was. It's now no longer spiking when you turn stuff off on and off on the other side of the workshop, but it does spike when you turn the spindle drive on the CNC mill on and off. Because although you can program a spindle on and spindle off for CNC, I had not implemented that. I just put a switch on there. And my buddy said, this switch you've got, did it used to belong to a budgie? Could you not have found something cheaper and nastier than that? Why do you not replace that with a proper switch? And while you're at it, you could put a 0-volt relay on there. You may know, I didn't know, what a 0-volt relay is.
A zero crossing switch.
Yeah.
It actually switches when the mains
Just like
goes
that.
through zero.
Yeah, exactly that.
I've got some if you want them.
Exactly that. No, well, I've got one now. Here it is. It's a, I mean, I knew what a relay was. This is a solid state relay mounted on a stonking grade heat sink. What it does is you give it a low voltage input, 12 volts or 5 volts or something, and you give it the low voltage and it switches the high voltage, the mains voltage, but it doesn't do it the split second you throw the switch. It waits until your 50 hertz sine wave is going through 0. And it does it, I mean, how clever is that?
I could do you a better price as well.
And as you see, it's pretty low cost. So he said, look, get yourself one of those and cobble that into place and get a better switch, for goodness sake. So I did get a better switch, and there's a picture of the better switch, which is actually a rotary switch, so it's like the one on a proper Bridgeport instead of a push button thing. And the other thing is that on the Arduino, we're back on the Arduino there, look, with all our steps and directions, and there is a pin that can respond to an NC program instruction to turn the spindle on or turn the spindle off. And hitherto it had not been doing that. And while I was doing this rotary switch and buying the 0-volt relay and feeling a bit sheepish about what David said about my old switch, I thought there is an opportunity here. There's an opportunity for me to, if I can get this organised, we could have a system whereby the 0-volt relay turns on if and only if both the physical switch is switched on and the program's switched on. And by the way, some of that oscilloscope trace that you saw earlier on was a switch bounce as well, my friend tells me. So he said, well, why don't you lash up something so that if both of those are switched on, it knows it's got to start, but it doesn't do anything for half a second or something. And then it has another look and it says, do you still want that? And only then, if it wants that, then it will run the spindle. And if either of those stop, if the program says, no, I don't want the spindle running anymore, or I turn my rotary switch off. If either of those happen, then it could say, well, hang on a minute, it's saying stop, but I'm just going to wait for half a second or some period of time. And then I'll look again, and if there still is a switch off signal, then I'll stop it using the 0 volt relay. Well, how are we going to do that? How on earth are we going to do that? Yeah, wait a quarter of a second, not half a second. So that was the plan. How can we do that? Well, I tell you what we did. The royal we, I got another Arduino, spent another £8.50 and implemented exactly what we said, and I promised that there would be computers but under control. And the program to do what I've just described was so simple that even I could write it, and it was about that long, and it does precisely what I've said, and that means, oh, and by the way, the electrical interference went away, more to the point, right? So we got the electrical interference nailed, but also it means that when there is a long program, like Jeremy's air horns or something like that, that's going to be several hours, I can make sure that the end of the program includes an instruction to switch the spindle off. I can let it run, and at the end of the program, when it's finished machining and lifted up, it will stop the spindle. So I don't have to go out into the cold snow. So electrical interference, all working, raise a glass to that. I don't have to go out into my cold workshop every half an hour to see if it's finished yet or not, because I know it's going to stop when I get there instead of running like an idiot with not doing anything. And I can be indoors in front of a roaring fire with a glass of muscle relaxant, and we're away. So that was the other problem, the other sticky problem that I wanted to tell you about. So there we are. Thank you for listening.